Olivier Pluchery, you are a professor of physics at Sorbonne University. Can you tell us what is bichromatics?
Yes, sure, of course. So bichromatics is a technology that uses the special coloring property of gold nanoparticle to use them in special materials. So what is really special with gold is that it's not yellow. It goes to vivid color like red, for example. And this could be used for inks, for painting, or for other kind of materials. And that will be useful for industry like the luxury packaging. This could be used also for the anti-counterfeit fighting industry. And so right now we are really working at making it into a product that will go to the markets, actually.
Is this your elevator pitch?
Yes, kind of, yeah. And so the typical elevator pitch, I don't know if you know what it is. That's when you are going to a building and you go into the elevator, you suddenly meet the investor you were looking for, or the CEO, an interesting CEO, and you have something like 30 seconds to explain him what is your business. And so, yeah, that's a good exercise actually. But yeah, bichromatics, I can show you some example. Like for example, here you can see some ruby red gold nanoparticle, just gold here, gold nanoparticle in water. We can do also with silver, and here it's yellow, but it's silver actually, silver nanoparticles. Here also that's gold particle with different shapes. They look like blue. And I can show you all range of color that we can create with this technology. So just wait a second. And for example, here, so these are small vial with gold on the right and silver and mix of both of them. And these are obtained with just gold on silver nanoparticle, and they are called plasmonic colors. And we can also have the very special effect of bichromatics, which is the fact that we have two colors. So here you can see polymer material that's in which we place our pigments. So it's blue when you look in transparency, and the really special effect that we have patented is it changes to orange or salmon color when the light is coming from is scattered, is reflected. And here you have seen typical bichromatic effect that we have created, and it's possible to do that only with gold or silver nanoparticles. But of course, in these materials, so we have worked a lot in the lab to create them. And so now I will talk a bit about the scientific foundation of this technology of bichromatics.
Yeah, could you tell us about the research part of bichromatics?
Yeah, so it's a long-term research, let's say, that began with this. So the easiest thesis we can consider is the Turkevich-French method, with which we can create 50 nanometer gold nanoparticles. And for example, here you can see we start with gold chloride, so gold ion, then we add a reducer, and when gold is reduced into nanoparticle, it turns red, like the nice ruby red you have here. And we can check with electron microscopy that the nanoparticles are actually of that size, basically spherical, and 50 nanometer, as you can see here on the left, on the right. Why are they red? Because everybody knows that gold is yellow usually. And the explanation of it comes from what we call plasmonics, so the special interaction of lights with objects that are much smaller than the wavelength of the light. And here we have this metallic nanoparticle, and we are going to look at what we call the extinction. So we look in transparency, And because of the plasmonics, this particle has a special resonance that will absorb one wavelength. And here it will absorb the wavelength that I've marked here, 520 nanometer, which is green. And so when green is absorbed, what remains is the red. And so that's the reason why we see them red, because the green have been absorbed. So this is the typical explanation of the red color of the nanoparticle. So this one. Then we also, so it can be applied to other noble metal, not all the metals actually, like silver and copper. It was also a bit. What is interesting is it's not new. It's known actually. It's known that gold can produce some very strange or vivid colors, and we have found some gold nanoparticle in the glassware made by Bernard Perrault in Orléans in the 17th century. So it was used as a luxury product for the kings, and so the rich people, let's say. The next century, so in the 18th century, it has been used for porcelain, and for the rose pompadour, as you can see here. And more recently, I have a colleague, chemist, who has used that to do some scarves and colored with gold nanoparticles. So this is the typical plasmonic effects. But what is interesting, is that's the heart of our invention or our patent, let's say, is that if you look not only at the extension here, but also at the scattering, the particle is going to scatter as well. So to diffuse light in other direction than the incoming direction. If we consider the previous particle, the small one, the one I call the small 20 nanometer in water, I have calculated here the extension cross section. So as I told before, it will absorb in 520 nanometer, and there is no scattering. So that's the green line, which is 0. If now I can make some larger nanoparticle, so 50 nanometer, you see that the green light is rising up. So there is more and more scattering. And if now I go to 100 nanometer, scattering is even smaller than absorption. So these big nanoparticle, the one I call big, so 100 nanometer, they are able not only to absorb, but also to scatter. And this scattering, that's the one who is going to give the other color. And that's the key of bichromatism. So bichromatism is typically an effect where my material will absorb one color and diffuse the contrary color, the supplementary color. And with this, you can create an effect with two colors. And again, this is possible only with objects that are large enough, like I have shown. And so typically with nanoparticle, and with, if you consider pigments, pigments are molecules, so they are nanometer size, so of the order of less than 1 nanometer, so there will be no scattering. So these effects has been understood quite recently, but what is, and what I can show you is how we have managed to produce this nanoparticle. So in my team, with the Bichromatics team here, so that's the work of Anaïs Lehou, who worked with me for a couple of times. And you see here the smaller one, and this we call the seeds, the 50 nanometer, the smaller one I discussed in the beginning. And then she is able to make them grow with different steps. So step 3, step 7 here. And with the size going to even the step 9, which is indicated here. Step 9 is 129 nanometers, so that's big nanoparticle. And with this, we can adjust the scattering power of this particle and have these two colors, I mean, to manage to control these two coloring property of the Bichromatics effect. Those of you who have worked with plasmonics, you all know the special example that I will show later. Just before this, I want to show you my latest experimentation with the optical microscope, where I was able to see individual nanoparticles. And here, each dot is a particle or a dimer or two nanoparticles together. And you can see the green diffusion power for the smaller one. And when the particles have different shapes, they will shine with different color. You can hear a light blue, red, here green and yellow. And this is given by the nanoparticle when you can control the shapes and the arrangement of them. I mentioned that there is really an intriguing example in history of art, which is the liquor gas cap that you can see here. So it's well known by the people who are working with plasmonics, because this cap is made, it was found that they were made with gold and silver nanoparticle. And when you illuminate this cap from inside, so you look at them in transparency, it looks like red. And when you illuminate from outside, it changes the color to green. And this is the most impressive example of the bichromatism. We have no idea how the glassmaker of the 4th century have done this cap. So far, it's really difficult to reproduce. And with the Bichromatics, we are providing a way to make it, more regularly.
So, what makes a color?
Okay, so yeah, that's a good question, because if you want to use this color for the market, for example, you will be asked to do this, for example, the red, ruby red, that this one, and this ruby red, you can measure it with a color chart. So for example, here, that's the color chart, which is known from RAL. And that color chart here, for example, that's the ruby red. Okay. But okay, I'm able to do this one. But now, if I want to sell it for a product, and if the next time I do not the ruby red, but the purple red, my client will not be happy at all. And so I should be able to reproduce it every time the same way, and with a tolerance which is really, really small. And this is not an easy task. And if you compare the two spectra of this, they're extremely similar. However, the eye is really able to distinguish them very clearly. And that's for that reason, if we want to use this color for the markets, we absolutely need to control and to understand the physical property of these colors. And with this, I will explain you a little bit more about these colors. So the eye, the human eye, is perceiving the colors through the cone cells with the three colors, more or less red, green, blue. And the actual color that you can see will depend on the balance between these red, green, and blue. And we would like to place this nanoparticle into the system of red, green, blue. And that's the basics of what we call the physical colorimetry, and that we had to tackle in detail for Bichromatics. And I just show you an example. So I took from that color chart the violet page, and I want to know how physically I can describe these violets. So to do that, I first record a spectrum. So here, in number 1, you see the color spectrum of these violets recorded in scattering. And then what the eye is doing is it's going to measure the balance of the three different color, red, green, blue, And this is the number 2 when you see the sensitivity of these three cones of the eyes. And with this, we are able to transfer that into the color coordinates, LAB, so and which are going to really put numbers behind colors. This is an issue that has been tackled by painter, by industry maker, by painter, also by many people, and to do a catalog, let's say, of all the possible colors. And so with this system LAB, that's a scientific system to put 3 numbers to describe a color. And just to make sure that I have done it properly, from this I could transfer this LAB coordinate into a RGB color that is displayed here. And as you see, it matches the origin. So I really know how it's possible to transform a spectrum into a color. So with this, we can go back to our issue at the beginning. So I can calculate the spectrum of nanoparticle, so I can predict the actual color. And this is what we have done with the Bichromatics know-how, the calculator. I will show you how it works. So it's an online calculator that's available for everybody. That's I need to share with you from here. Okay. So here I'm going to consider a homogeneous silver nanoparticle. So I choose silver here. I can choose all these materials. So you can access that online. You can play with it if you want. I will just play with 50 nanometer, I will 60 nanometer, let's say, to change. Silver nanoparticle. So I have the spectrum that is updating here. I place that in glass. Glass will be 1.5 in optical index. And then I will place this into materials of 50 micrometer of thickness and with density which is 1 nanoparticle per cubic micrometer. With this, it's possible to calculate the transmission spectrum and the scattering spectrum, and also the color. And you can see that in transmission is going to be yellow, and scattering is going to be blue. And so with this, we can adapt, change the thickness, for example, and see how the color is changing. And that's a good way to really predict the color we can get. And so that's one part of the knowledge of the Bichromatics. And with this, we were able to design the color charts, the beginning of the color chart of Bichromatics. For example, using 20 nanometer nanoparticle, the small one, there is a pink transmission, pink or like red, and black scattering means no scattering. So it's not Bichromatics. So when I increase the size, I'm going to 60 nanometer, I start having different color in transmission and scattering, and so on. Blue, and here salmon color. And I can also do that with silver. And silver, you can see there are very different colors with a light yellow here and light blue on the other side. And so this is really, this is not the 200 color that I have in that chart, but that's the beginning of it.
Have you sold any products yet?
Okay, that's it's an interesting question. Let's say so far we have not sold any product, but we have done what we call the proof of concept POC that you can see here. So we have worked with a designer who is selling lamps for decoration, and we provide her with this small parts that I have here, which is Bichromatics. And you can see clearly, so you have the video here that you can look at. I will not show it right now. But you can see that it looks orange here and the shade is blue. And with this, so it's a very nice lamp that is projecting shades in your home, and with this Bichromatics color that you can arrange by yourself. And that's really a proof of concept of the thing we can develop with Bichromatics. And so now, Troy, that's the question. we have not sold any product yet. We are targeting several markets, and so the pigment for the luxury packaging, for example, there is interest also from the cosmetic and makeup markets. We have talked with people from the automotive industry to design special parts of luxury car, and so there are some possibility there. And we have also discussed about the anti-counterfeiting industry, where it could be very interesting to have this patented, not easily reproducible system to protect the genuine parts you can sell. But when you ask this question of what markets, you have to answer the question of what kind of revenue you want to get, of course, how much money you can make from it. And it's a question we don't like so much when we are scientists, actually, but if you want to live from this, you have to ask this question. Here, I take an example of the La Petite Robe Noire, so a bottle of perfume from Guerlain, that I like especially because the color here is properly done by metallic nanoparticle and plasmonic effect. So it's a good example of actually product on the market based on plasmonics. And here, if I wanted to do the bottle, the cap of the bottle, I could do that in Bichromatics, for example, and knowing that one bottle of this perfume is sold something like 50 euro, I could hope having from I could hope that I could sell my cap to the maker of the perfume, maybe 50 cents or 1 euro at max. And if they are doing a good sale, they will be able to sell maybe 20,000 of this bottle. And so if you make the calculation from this, I will get 10,000 euros. And just imagine having sold 10,000 of these products, like based on that kind of things, and receiving just 10,000 euros, the market is nothing. And sure, so that's big issue to find really the right market when I could pay at least 2 salaries. And so one salary is at the beginning will be 40 or 50,000 and as an employer. So that question is really the question that has to be tackled really seriously. So far, we have a beginning of answers, but it's not complete yet. When you ask about making a startup, making money, there is the question of the money. So we have started this experience in 2015 by patenting the Bichromatics effect, and this costs something. So filing a patent is something like between 10 and 20,000 euros. And then we have asked the CNRS to support us. He refuses because, yeah, for many reasons. Then we had very strong support from the SAT UTEC, which is a society that helps our university to go to the market. I placed in green the successful help with money or salaries, and in red the one that was refused. I will not go too much into the detail here, but we could hire one engineer for 1 year and a half, and then another one for 6 months. And with this, we were able to really push that technology. But yeah, now we are not yet on the market, and we still need money. But money, is not the most. Yeah, it's an issue, but that's not the most delicate one so far. There is a question of time. Of course, we began 5 years ago, and we are still running to get some product to improve the technology. During these 5 years, I had many. So we my team, actually, that you can see on the photo here. We have participated to many professional exhibitions to meet people, to test our products, to see if there are some interest from different industry. And we have established many business contacts here, and that's one of the most important things, to test the ideas, the technology with very different people. So some people were taking this very seriously, some other were laughing at us actually, because yeah, they doubt that we can go to the market. So there is a real challenge here, and to prove the contrary. So patience is one of the key. Patience, and not only is to wait, there is a right moment where all the stars will be aligned, and so that's the moment to really kick off the startup. And very important thing when you want to do this kind of technology development is, of course, the people. So we were 3 at the beginning to file the patents, to start the patents, Delphine Channing, Intremita, and myself. And then we get the first funding, and with this we could hire Anaïs Lehoux, who was engineer and developed a lot the chemistry of the synthesis for the nanoparticle, the big nanoparticle, as I show you, how to place that into a material. Then we had a small internship with Arik Grell, and then a big push with the arrival of William Watkins, who take up from Anaïs' knowledge about making nanoparticle. He succeeded to place that into polymers like this. And at that time, so last year, we really wanted to make the start. So I was looking for associates to work with William and to really start the company, because if you want to start something when you are alone, it's not really safe, let's say. So I didn't find an associate, and William went to another business, and so now I'm again in a phase of searching associates. In between, in my lab, we have hired Johan Prado, who is working a lot on gold nanoparticles. So we have this chemical knowledge, and we have this physical knowledge of about the colors. And so now we are ready to go to the next step, which is this one. So Bichromatics is now recognized, so acknowledged as for its expertise in colors, plasmonic colors, in the color of gold. And so for this, I'm doing consulting actually, and that works quite well. But on a longer term, we are also looking for industrial partners to develop this technology further and to develop to a given market. So here I place 2 of them. One which is coming from a company I really like, Dacryl, who is doing some very nice decorative work for restaurants, for rooms, for hotels, and playing a lot with the colors. And for sure, we could bring a lot with a Bichromatics effect in this kind of decorative arts. And another important possibility is to work also with the painting industry, the ink maker, because we know how to do these very special pigments, and that could really bring a huge value because they are non-toxic, because they are really permanent. Gold is eternal, it's known, so it's still the case when it's nanoparticle. And plus this bichromatic effect, it's probably very interesting for coloring with unexpected effects. And so we are still interested with the collaboration, and we are really open to work with the industrial partners. We have several now discussing with them. And so that's it. I hope with this you will invest in Bichromatics in the future year, and I'm still open for the discussion. Thanks a lot.